Hi everyone, my name is Chen. I came from Nanyang Technological University. Today I'm going to present you our work, APICraft. This work focuses on generating fast drivers for closed-source SDK libraries. This is a joint work from Nanyang Technological University on the financial company and the University of Science and Technology of China. Well, closed-source SDKs are the basis of nowadays software. For example, the SDK provided by the Windows OS or the macOS. They contain huge attack surfaces. Since they are not the traditional command line programs, security experts usually have to manually create some wrapper programs or fast drivers as the entry points for the fast testing. Some researchers have already tried to automate this process on source code available scenario, leaving the closed source cases underdeveloped. Well, there are two main challenges. First, there are limited information that can be used in this kind of binary only scenario. Second, we also need to keep the semantic correctness for these complex API usages. In other words, to generate fast drivers for closed source SDKs, we need to answer two questions. What kind of information should be collected and how to utilize this collected information? Well, we're first going through the fast driver generation process from a human expert's perspective. The top half of this slide shows the source code of two consumer programs, which uses the target library's APIs. We use numbers to represent the different API function calls. If we directly extract the execution sequences of these two programs, we can get two fast drivers that are shown in the subfigure A. Well, to test more coverage, we try to cross over these two sequences to trigger more program behaviors. For example, both the outputs of 1 and 4 can be used as the input of 2. Therefore, we can exchange their subsequences of 1 and 4. After this kind of crossover operations, we can get some new fast drivers shown in the subfigure B. And the ideal fast drivers of these two programs are shown in subfigure C. Comparing these results, we can conclude that this kind of crossover strategy cannot give the best answers, since some crossovers can produce redundant fast drivers, and some API calls can be merged into one fast driver, like the functions 3 and 5. Both of them are uses the output of function 2. Well, intuitively, to find a better or best answer, we can first learn a set of basic dependencies between API calls and then uses a search-based approach to explore better combinations of these learned dependencies. Well, our work, APICraft, follows this basic idea and systematizes and automates the whole process. Well, APICraft proposes a collect and combine approach and has three key components: the pre-processing component, the dependency collection component, and the dependency combination component. Well, the pre-processing integrates both static and dynamic information of the target SDK from multiple sources, including the header analysis, the static binary analysis, and the execution trees of the consumer programs. Well, these information are further integrated as two parts: the metadata information and the execution trees. Then, in the dependency collection stage, APICraft learns possible data dependencies between API functions from traces and control dependencies of each API function. Next, APICraft uses a multi-objective genetic algorithm to direct the combination of these learned dependencies. During the combination, each generated candidate fast drivers will be evaluated based on three key metrics describing their static and dynamic performance. Finally, the winner candidates are the generated fast drivers. Well, we briefly review several key details of the APICraft. We collect two kinds of dependencies, the data dependency and the control dependency. For the data dependencies, we design a specific algorithm to extract the possible data dependencies between API functions from the sequence from the execution trace. Well, we called this basic data dependency extraction. Since the learned dependencies can be limited by the traces, we further propose several heuristics to infer new dependencies from the observed ones. We use 3 rules. Rule 1 is dependency-based transition. Let's say this can be pronounced as FA to FC, and it means that one of the output of FA can be used as one input of FC. Well, if we observed FA to FC, FA to FD, and FB to FC from the traces, we can guess they possibly have a FB to FD. Well, rule 2 is type-based transition. If we observed that from the learned data dependencies that one of the output of FA is type T, and one of the input of FB is also of type T, we can guess that FA's output can be used as FB's input. And rule 3 tries to find the data dependencies between the threads. The basic observation is that the threads exchanges limited data, and usually they exchange pointers. We want to dig some data dependencies from this kind of data exchange. Well, for the control dependency, currently APICraft only collects error handling information of each API function. Well, for each output of an API function, we naively conduct a no pointer check for pointer type output. And for integer type output, we propose a tand-based analysis to extract its check condition. Next is the combination stage. For the dependency combination, APICraft uses a search-based bottom-up approach to search a better combination of data dependencies. We identify 3 important and independent metrics for evaluating a generated fuzz driver. And then we use this multi-objective genetic algorithm to guide the combination. Well, these 3 heuristics are first the DIV, the diversity. This measures the degree of the used unique data dependencies. The higher the DIV a fuzz driver has, the more unique or more complex data dependencies the fuzz driver will contain. Well, EFF, the effectiveness, intrinsically EFF is the weighted basic block coverage. The higher EFF a fuzz driver has, the more core logic of its called API functions will be triggered. Well, compactness, COMP, it represents the simplicity of a fuzz driver. It calculates the degree of redundant or unnecessary data dependencies that a fuzz driver contains. Given 2 fuzz drivers candidates that has similar scores in DIV and EFF, we prefer the simpler one. Well, besides these metrics, APICraft further uses 2 techniques to evaluate and improve the stability of generated fuzz drivers. During the evolution, APICraft compiles each generated fuzz driver with sanitizers and then do the smoke testings with several prepared input files. Once the stability test fails, that fuzz driver will have 0 score on all 3 key metrics, and it will be abandoned in the next round. APICraft also uses learned control dependencies to generate error handling stubs for some API function calls. This technique significantly improves the stability of generated fuzz drivers. Well, now comes into the evaluation. We apply the APICraft into 5 attack surfaces of macOS SDK and get the traces from macOS built-in applications. The traces are in GB level, and the learned dependencies for all attack surfaces ranges from thousands to hundreds of thousands. It proves that APICraft can apply to real-world closed-source SDKs like the macOS SDK. Well, we also conduct repeated 24-hour fuzz testing experiments to compare APICraft generated fuzz drivers with its manually written counterparts. The results show that in most targets, APICraft outperforms manually written fuzz drivers in both coverage and crash with statistical significance. And we also analyzes the effectiveness of APICraft's each component. The result shows that each component significantly contributes to the overall performance. Finally, we set up an 8-month long-term fuzzing. In total, we found 142 unique vulnerabilities, and we got 54 CVEs. These vulnerabilities affect popular Apple products and several Apple OSs, where all the found bugs are confirmed and fixed by the vendors. This is the end of my presentation. Any question is welcomed.